I'd like to start by thanking the organizers for giving me this opportunity. So I'm going to talk about some emergent properties of interacting active matter, and this is based on some recent works that and some ongoing works that we have been doing in our group with two PhD students, Ritik Sarkar, who is here, and Debraj Dotto, and Shreya Chatterjee, who is a PhD student currently in Germany. So I don't need to introduce active matter to this audience, of course. So these are particles whose dynamics is inherently out of equilibrium, and they show a lot of novel collective behavior like swarming, flocking, clustering, etc. So one key feature in this phenomena are that their tendency to cluster together. So even in the absence of any underlying interacting potential, they show an emergent attraction. And an important question is how to understand this quantitatively from a microscopic picture. So this is a hard problem, and the starting step is to study just two particles and look at the effective interaction. So there have been some studies over the years on this, particularly on the behavior of a pair of run and tumble particles in various contexts, like when they have short range repulsion or attractive coupling or finite tumble duration. So for example, Abhishek Anupam with Orgho did some work, also Shotto and Gregory with PLA Diswal, they did some recent work. So the common picture that emerged from these works is that irrespective of the underlying condition, these particles show an emergent attraction. So the question we are asking here is that is it possible that for active particles to repel each other? And the answer turns out to be yes, and somewhat surprisingly, it is possible when they are coupled attractively. Okay, so let me come to the model directly. So we are considering n active Brownian particles. So these are particles which have an internal orientation, and that orientation diffuses, and we consider pairwise long-range attractive potential VR. So the ith particle moves according to this Langevin equation. This is the force from all the other particles, and this is the self-propulsion force. And each particle has its own self-propulsion speed Vi. And this Ni is the internal orientation, so it's characterized by an angle theta, which undergoes this diffusion. So we start with the simplest case where we have two particles and harmonically coupled, so the potential is this, and we look at the statistics of the separation of the two particles. So this separation evolves according to this Langevin equation. So it's very similar to one particle in a harmonic trap of strength 2k, but the noise is a little bit different. Okay, so this eventually reaches a non-equilibrium steady state, and depending on the relative strengths of the time scales in the system, this non-equilibrium steady state actually shows a lot of interesting features. But what we are going to concentrate here is on the strong coupling regime, where the coupling strength K is much larger than this D1 and D2. So this is a simulation of this particle motion in the center of mass frame. So if you look carefully, you will see that these two particles never come inside this circular region. Okay, so they must maintain a minimum distance from each other. And this scenario emerges only when their self-propulsion speeds are different. So this is like an emergent repulsion because they cannot come very close to each other, even though they have an attractive coupling. So had these been passive particles, they were most likely to be near the origin, to be together. Had these been active particles with same speed, then also they are most likely to be near each other. Okay. So we tried to understand this analytically, and it turned out that in the strong coupling regime, we could calculate the stationary distribution exactly. And it turns out that indeed there is a minimum separation. That minimum separation is proportional to the difference in their self-propulsion speeds. And that disappears for V1 equal to V2. So there is an emergent repulsion just purely from this difference in their speeds, and also because of the fact that they are coupled attractively. So this is a plot of the radial distribution, and you see that below this minimum separation, the probability is exactly 0. The symbols are from simulation. So we could calculate this. So this is a scaling form. This distribution follows the scaling form, and we could calculate the scaling function explicitly. Also for the marginal distribution, marginal x component, here the repulsion is apparent in the form of peaks which are away from the origin. Also, if we look at the 2D distribution, it is confined in an annular region. And there is an empty excluded region in the phase space, which is again is a signature of this emergent repulsion. So what we have seen so far is that active particles, if they are coupled attractively strongly enough, and if their self-propulsion speeds are different, then there emerges a repulsion. Okay, and the physical reason for this, as far as we could understand, is that because of this difference in the self-propulsion speeds, there is a push which is generated between the two particles, and that push makes them stay apart. So now, I mean, the question is, how robust is this phenomenon? Can we see this is it specific for two particles, for harmonic coupling, for long range interaction, etc.? So the answer turns out that it's quite robust. So it survives even when they are coupled non-linearly. It survives even when there are many particles. So each pair actually, feels this repulsion, and also when the force is short range. So I'm just going to quickly show you the short range case because this is very interesting. So once again, we consider a collection of n ABPs. Now the potential is short range, it's a truncated harmonic potential. So there is a range R naught up to which the particles feel each other. And we consider n1 particles with speed v1 and n2 particles with speed v2. So there are two classes of particles there. And what we see is that then there are different phases emerging in the system. When the range of the interaction is very small, then they move randomly. There is no ordering, they just move uniformly and randomly. Now, when the range is increased a little bit, then the slower particles come together and form a ring. So the faster particles are still moving around randomly. So this we call a partially ordered phase. And then if the range of interaction is increased even more, then we have this two ring structure. Slower particles form this inner ring, faster particles form this outer ring, and the separation between these two is again coming from the repulsion between the two particles. And just to note this fact that this R0 need not be so large so that all particles are seeing each other. Even before that, we are seeing this fully ordered state. So we tried to understand these three phases, and Debraj was able to calculate the boundaries of the conditions for emergence of these phases. So these are the ranges this is a competition between number of particles and range of interaction, and these are the three different phases. So we also measured something like an order parameter because we want to sort of quantify this phase transition. So one measure is just the inverse of the radii of these circles, and this is the order parameter diagram. So as we increase the range of interaction, this first ordered phase, partially ordered phase emerges, where this one order parameter is non-zero, the other one is still zero, that's the outer ring. It is not formed yet, and then we have this ordered, fully ordered phase, and this is the phase diagram in R0n plane. And so I'll just conclude. So what we have seen is a novel kind of phenomenon emerges when we have this heterogeneity heterogeneity in the speeds of active particles, and it's quite general. It doesn't depend on what particular kind of interaction we take, as long as it's attractive monotonically increasing, and it doesn't depend on what particular kind of active dynamics we took. It's also expected for RTP or other kinds of active processes, and we also see the emergence of a novel collective behavior in the sense of this ordered and partially ordered phases. And of course, we still need to characterize these phases. This is still ongoing work. So I would like to finish here, and thank you all for your attention.
Thank you so much for the talk. We have time for question answers now.
Hello. Hi, ma'am. Very interesting talk. Thank you for introducing this. Yeah, I'm just curious, like why they form two different ring.
So this is because they have different speeds.
Okay.
So so basically the radius of this ring is decided by your speed.
That is the only input variable you are using?
Yes. And so it would also depend on the ratio of the number of particles. But as long as, so suppose we have three different speeds, then there will be three circles.
So did you also check with increasing packing fraction how it will go?
Yes.
Number of particles?
Yes. So for example, I did not go into the details of this. So this is the phase boundary, so to say. So this number RC, that depends on the ratio of the two, N1 and N2.
Okay. Thank you, ma'am.
Hello.
Yeah.
So if you have a distribution of speeds instead of just two delta functions.
Yes.
So there's a sort of clustering of large speeds and small.
So we expect that. We haven't checked that yet, but we expect that there will be sort of a gradient in the this forming thing.
It's an interesting
Yeah.
talk. Just one question I have. You said that the velocities of the two particles, V1 and V2, because they are different, it generates a push. Can you please explain the mechanism of the push? I suppose the two velocities are constants you are taking.
Yes, yes.
how
So
is
the
the push
mechanism
generated?
of the push is, this is very simple. So what we have is this dynamics here. So basically the boundary of this thing comes when this r dot becomes 0. So before that, so this force is the attractive force, and the net force that is pushing them out is the difference between the two. So that's the net push.
No, so you are saying, so if one generalizes it for run and tumble particles, so you are saying that if they have different speeds, and so will you see this thing if they have different tumbling rates?
No, the different tumbling rates would be like different d1, d2.
Okay.
It's not coming from that.
So it's only if the speeds are different for RTP
Yes,
particles
yes.
that.
Yeah, yeah. I mean, different tumbling rates would give you some other effects, but not this particular one.
Okay, thank you.
Any other questions?
Yeah.
If
Yeah.
So are they interacting among each other? We like two species of particles. There is no interaction.
Yeah, they're coupled attractively.
So they have attractive.
They have attractive coupling. That's why that.
They are in a harmonic.
No, there is no global harmonic potential. So they are just attracting each other. There is no global potential. So the center of mass actually moves freely unless you put them in a box. So this is the equation for center of mass for two particles. For the many particle case, we put the whole system in a box so that there is a stationary state always. But it's only a pairwise attractive thing.
so much, let's thank the speaker.